Next one is the relation between the autocorrelation and power spectral density. As we have just seen that the autocorrelation can be written in terms of as a summation from minus infinity to infinity mod of fn square e power jn omega naught tau, which is in terms of the exponential Fourier coefficient fn. Therefore, what is the relation between the autocorrelation and power spectral density is, when we take the Fourier transform of this autocorrelation function, it will be our power spectral density S of omega. This is our autocorrelation, this was our power spectral density S of omega. That we need to prove that. That's why take the Fourier transform of the autocorrelation function, that is R of tau, which is being given as summation from minus infinity to infinity mod of fn square e power jn omega naught tau. For this entire thing, we need to take the Fourier transform. That's as a summation we can kept it outside. Summation from minus infinity to infinity mod of fn square will be out, and taking the Fourier transform of e power jn omega naught tau. Therefore, the exponential, what is the Fourier transform as? It is the 2 pi into its delta of 2 pi into delta of omega minus n omega naught. Here, because of the omega naught, it will be the delta of omega minus n omega naught. This entire thing is nothing but our Fourier transform of R of tau, which is nothing but our S of omega. That the Fourier transform of R of tau is S of omega. Okay, that is the relation between the autocorrelation and the power spectral density. Similarly, the relation between the convolution and correlation. As we know that the convolution between the two signals x1 of t convolution with x2 of t will be given as from minus infinity to infinity. The first one as x1 of tau, x2 of t minus tau, and integration with respect to tau. How we'll get these options is, the first signal will be written in terms of tau, and the second signal will be written in terms of t minus tau. That's in the first process, that is t will be simply replaced by the tau, and here for the second case, the first we should take the t, then it will be followed to the tau. Later the tau will be time reversed, that's why tau will be changed to minus tau, then add t units to this minus tau, therefore we'll get the t minus tau. That will be used for the second signal, and integration with respect to the tau. Similarly, the same process will be done for x1 of t convolution with the x2 of minus t. That's minus infinity to infinity. First signal will be written as this, that is x1 of t will be written as x1 of tau. For getting the second function, and integration with respect to tau only, for getting the second function, follow this sequence of order. First here t, that's why we have taken t. Here minus t, that's why take the minus t. This t will be changed to tau, therefore the minus t will be changed to minus tau. Later the time reversal operation, tau will be changed to minus tau, and the minus tau will be changed to tau. Later it will be changed by adding the t units to the minus tau. Therefore here also add the t units to the tau. Therefore it will be t plus tau. That will be presented here. Therefore we'll get the t plus tau. Then this was the keep it as our first equation. As we know that R12 of tau will be equal to, it will be given as from minus infinity to infinity, x1 of t, x2 of t plus tau, and the integration with respect to t. Simply point is that if you observe these two equations, these two are being equal when our x1 of t convolution with the x2 of minus t at t is equal to tau. If we put the t is equal to tau, that means tau will be replaced by t, therefore we'll get this one. Here also t will be replaced by tau and the tau will be replaced by t, like that. Therefore we'll get these particular equations, which is nothing but our R12 of tau. That is the relationship. The convolution between the x1 of t and x2 star of minus t at t is equal to tau will be equal to R12 of tau. Okay, that's the basic relation between the convolution and the correlation. This is the cross correlation between 1 and 2. This is the correlation between the convolution between the 1 and 2. This is the cross correlation between the 1 and 2 signals. This is the convolution between the x1 of t and x2 of minus t.